Okay, so lecture A1, complex functions. So I wanted to review this before we did lecture 5.2 because in lecture 5.2 we're going to really want to have a good intuition for evaluating complex functions, and in particular we want to have a good intuition for the geometric interpretation of the evaluation of a transfer function at a given point in the complex plane, at a given test point in the complex plane. So we'll unpack that a little bit. But first of all, you may not have seen a ton of complex functions in the past, so let's just do a little definition. I am going to skip over parts of this lecture because we don't need to do contour mapping until we get to control 1. We're going to do Nyquist plots and control 1. If you don't do control 1, then Nyquist plots are cool. You might have seen them in instrumentation class, but construction of them is not going to be until control 1. So we won't need to learn how to map contours per se through the transfer function yet. So okay, so a complex function f maps a subset of the complex plane to the complex plane. So it just takes complex number and returns a complex number. For instance, a complex function f can map a single complex number s0 to another s1 by just plugging it in. So just plug in s0 to the function, you get s1. They're both complex numbers. Great. So it works as the usual complex, or the usual function works, real function. Put in a real number, get a real number. If you put in a complex number into a complex function, you get a complex number back. Even if that complex number is just a real number, because the reals are just a subset of the complex plane, right? So, great. So we're going to skip the stuff about contours and curves. Complex functions are of interest in control theory because transfer functions, one of the central mathematical objects of control theory, are complex functions, okay? S is a complex number. H of S can return to you complex numbers. And so it is a complex number going in and coming back. So the utility of evaluating and mapping contours with complex functions arises especially in root locus design and frequency response design, especially for Nyquist stability criterion, which we're not going to consider in this class. So, quick example of mapping a complex point. So map the complex point s equals 1 plus j3 with the transfer function given below, h. Sometimes we say that we are evaluating the transfer function at the point s equals 1 plus j3. So it's a simple application of the concept of a function. H of 1 plus j3, wherever you see an h in the transfer function, you replace it with the 1 plus j3. So 1 plus j3 plus 4 over 1 plus j3 minus 1. And the 1's cancel. You have a j3 on the bottom. You could multiply it by j over j if you wanted to give yourself 1 minus j 5/3. We could also use a polar form or phasor form of the complex numbers too to combine them. That would be fine as well. So that was just a simple mapping of a single point, complex plane. NBD, right? Okay, so this is the part. This is the payoff for us for what we're going to be doing on Wednesday. So geometric interpretation of complex functions. It is often helpful to interpret the complex mapping of a point or a contour geometrically. Let us consider a transfer function, h of s, with complex zeros, zi, complex poles, pj, and real scaling factor k. Considering each factored term of the transfer function in terms of its magnitude and phase, we can write the magnitude and phase of the transfer function as follows. So the magnitude of the transfer function is equal to the magnitude of the gain times, it's going to be the product of, so the big pi product over I of the S minus Zi terms. So imagine that the numerator was factored into S minus each 0. And then we want to take the magnitude of that. You can take the magnitude of each factor, right? So magnitude of S minus Z1, magnitude of S minus Z2. Take the product of those magnitudes together, we would get the product, or we would get the magnitude of the numerator. The magnitude of the denominator is the product over J of the magnitude S minus Pj. Cool. So that's so this is just like in phasor discussions when we would multiply and divide magnitudes, right? If you take the magnitude of each term and you multiply them together or divide them, it works just like with phasors. If you want to know the phase of the transfer function, you have to take the sum, right? The sum of the phase of S minus Zi minus, the poles come back negative, so minus the sum of all of the poles, Pj. I can't say Pj without thinking of the Wyclef song. I would play it, but then I'd probably get this video taken down. So I don't want that. I don't want that, but it's good. I like it. I mean, it's true. Why didn't you bring cake? Actually, I care about the ice cream. And what?
I was probably frowned upon.
By whom?
Yeah, she wasn't here though.
Okay, so we can interpret this geometrically as follows. So what we're going to do is, okay, so we just saw the magnitude and phase criteria like 5 seconds ago, right? Magnitude of a transfer function, phase of a transfer function, okay? So that's what we're going to circle back to in a minute. We want to come up with a geometric interpretation of a magnitude of the transfer function and the phase of a transfer function in terms of its poles and zeros. That's what we're going to do right now, and it's a little bit subtle, but I encourage you to really invest in understanding this. It's going to be worth it. It'll pay off. Okay, it's worth it. So we can interpret this geometrically as follows. Let's consider the evaluation of the magnitude and phase of a transfer function at a specific complex value psi. So we're going to say S equals psi. Okay, S equals psi. The differences, psi minus Zi, which show up in the numerator in the magnitude, and they show up in the first term here in the phase, and psi minus Pi, so psi minus the poles, which show up in the denominator of the magnitude and then in the subtraction of the phase, can be thought of as vectors in the complex plane with tails at Zi and Pi and heads at psi. So let's unpack that for a second. We've got the complex plane. If you think of things in the complex plane as being vectors, then an object, a complex number, let's say like 2, well, I'll say 2 plus J2. This is 2, and this is 2. This is the real axis, this is the imaginary axis. If you think of that as being a vector, say equivalent to like column vector 2, 2, for instance, then we can do things like vector addition and vector subtraction using complex numbers. Okay? So if you think of a subtraction in terms of a vector, so a subtraction in terms of complex numbers, we can think of it as being analogous to a subtraction in terms of a vector, right? So psi minus zi would be this vector in the complex plane with tails at the z's and p's and heads at psi. So let's look and see how the magnitude and phase would look geometrically then. So if we say that our poles are going to be at -3 plus or minus j3, and we have a 0 at 1, and this is our psi, then this is how we could interpret the evaluation of our transfer function, is that we've got these poles, and this red thing is psi minus p1. This red one is psi minus p2, and this is psi minus z1. Okay, those are those vectors. And the length of this, that length is going to be the magnitude of psi minus p1. And this angle, which is kind of hard to see, that angle is the angle of psi minus p1. And this length is the magnitude of psi minus p2. And this angle is the angle psi minus p2. And finally, this length, well, that wasn't very elegant. That length is the magnitude of psi minus z1, and the angle is the angle of psi minus z1. So, what we've got here are the lengths of these. So the length of this guy divided by the length of this guy and multiplied by this guy gives us the magnitude within k. K is also multiplied there. And then the phase is just this phase minus this phase minus this phase. So this geometric conception is going to really help us when we start to construct the root locus in a minute, because we're going to have the magnitude having to be equal to certain things and the phase having to be equal to certain things in order to meet the root locus criteria, right? The magnitude and phase criteria. Okay. So this evaluation, this thinking in terms of the vectors and the, evaluating a transfer function in terms of its poles and what is the argument, what is the test point psi, we're going to be able to say, okay, like this guy up here, this point, this is either on the root locus, so it either is a solution of the for the closed loop poles, or it's not. And we're going to have certain criteria that we'll use, the magnitude and phase criteria, to help guide us to know if this point is on the locus, we will say. It does have locus, we'll say, or if it does not. Okay? All right. Congratulations. This is the subtlest mathematical thing we'll do in this course. So if you follow this, you're good. You're good.